In software engineering, we are taking chapter number 30, product metrics. So it's all about the software, and we would like to discuss certain metrics. But software involves various processes in software development lifecycle. So the metrics related to process are process metrics. Finally, software as a product with all the deliverables. Then we have the metrics, and software is made in a project. So that project, all the estimations, all the values, empirical discussions, that will come under the project metrics. So what we are going to discuss is the metrics can be project based metrics, and it can be design based metrics. The project based metrics, as I just showed you, process, product and resources. In the design based, the traditional or the conventional softwares we were using. And then the second type is the object oriented, where the object is the key. So the design based metrics on traditional can be the cyclomatic complexity, it can be the line of codes, the CP, etc. All these we are going to discuss. Along with this, the object oriented like the CK and mood, this also we are going to discuss. In software world, we know that we have number like 5 volt or 3 kilogram or say 21 degree centigrade. These are specific value, and you can directly measure these values using various devices, instruments. But the problem in the software world is because it is still evolving, and previously we were making conventional software, then object oriented, now web apps, and now mobile apps. So things are changing so fast. Direct measures are quite uncommon in software world, but still we need to measure. So we will discuss the measure that can be employed or used to assess the quality of the product, or you can say the software or the application or any app as it is being engineered. That is, we are talking about quality here. So we would like to measure. Until we measure, we will not be able to understand the attribute or what is the qualities. So these measures of internal product attribute provide us with certain things. As I said, the product when it is being delivered or about to be delivered, before that we need to measure certain things. First is, in the software life process, we have requirement engineering, requirement modeling, then we have design and architecture, then the code modeling. So this requirement, design and the coding, these measures will give you a real-time indication of the efficacy of all this. When we will write the test cases can be employed to any work product generated during the life cycle of a software. So what is the effectiveness of these test cases? We need to measure it, whether it is good, whether it is bad, whether we can employ it, are these test cases going to work, and the overall quality also. Measures, metrics and indicators. These are the three things we will be talking, and they are quite close to each other. Measure, the measure is mark. Measurement is mark now. Okay, let me tell you. The measure, it provides a quantitative indication. That is, we are talking about a number. So measure will give you a number, a value. So this will give you a quantitative indication of what is the extent, what is the amount, what is the dimension, what is the capacity or the size of certain attribute or a property of a product or a process. I hope you got the idea. This measure will give us a number of various aspects of certain attribute of a product or a process. So these attributes can be multiple, like the completeness, like the efficiency, like the reliability, like the availability. So these are what I have spoken are also the quality attribute. Now the measurement is the act, is the work of determining a measure. What is metrics? Now IEEE gave a very good definition for metric. This metric is a quantitative measure of the degree. So here degree has come. A quantitative measure of the degree to which the system or a component or a process possesses a certain attribute. For example, take the example of reliability. Now this is an attribute of any product or a software. So the quantitative measure of the degree to which the system, so just understand we are talking about a system or a component or a process. Now, it can be anything. So this reliability in that system or a component, what is quantity measure of the degree to which this attribute is present in that component. So this matrix relates the individual measure in some way. Okay. When we are attending or we are collecting a single data point, let me take an example of a software component. Now we need to test it. There are certain errors will be uncovered. So when we take a number in a single software component, these numbers of error has come. We have established a measure. What is a measurement? This is the one data point we have just collected. But now let us move to more data points or more collection points, more way of collecting. So same component, when we are able to do it in multiple ways, for example, we have same component, we are doing the reviews, say the technical review. And then this can be done multiple times, or say unit test we are doing. So the number of component reviews and the number of unit tests, now we are having multiple data points, and this is also we are using to collect the measures of the number of errors for each. So here we have two data points. Previously it was one data point. Okay. So when we establish the measure, then we go to multiple data points in order to collect more data, and this becomes a measurement. When we have multiple data points, it becomes measurement. So a software metric relates the individual measures in some way. How do we relate? For example, we found some certain errors. So the errors found per review, and what is the average of these errors? That is the number of error per review. What is the average value of these errors per review is a metric, or the number of errors per unit test. What is the average rate? This is a metric. Okay. Now indicator. Indicator is when we take a matrix, or you can say combination of these metrics that provides us with the insight into a software processes or a software project. So indicator will indicate through certain combination of values, and this indicator is why we are calling it as an indicator, because it is going to indicate the software team, for example the project manager or a software engineer, that this is the indication, this is what you are getting, this is the number. And on the basis of this, for example 4 is there, you need 2, 5 is there, you need 3. So now the project manager can adjust the process and project on the basis of these indicators. Measurement principles. Now Roche, he suggested a measurement process is characterized by certain activities, namely 5 activities. So in order to do a proper measurement process, first formulation has to be done, collection, then the analysis, then the interpretation, and finally the feedback. So these are the steps you can say, or these are the activities involved for a proper measurement process. That is what we want to do. Then we will collect the information or the data. Then we will try to analyze what we can do with this, in which way we can use it. Then we interpret, that is quantitative way, and then we will give the feedback to the person or the people which are concerned. So the metrics, there are certain principles also, how to characterize the metric and also how to validate these metrics. Because metric cannot be just thought in a dream. You have to have certain properties for a metric. For example, a metric should have a desirable mathematical properties. It cannot be subjective, it cannot be objective. Metric value should have a meaningful range. Okay, that is, for example, you say 0 to 1, what does it mean? 0 may mean absence of certain attribute or degree of content, or you can say 1 is the presence. If minimum maximum we are saying 0 is minimum, 1 is maximum. So 0.5 will be what? It will be halfway point. So mathematically it can be defined. And the increasing and decreasing nature, when a metric represents a software characteristic. For example, we are taking example of usability. Now when it is increasing, the positive traits are occurring, it is increasing. When undesirable traits are occurring, it is decreasing. So in the same way, corresponding way, the matrix should also increase and decrease in the same manner. That is, it should show the correspondence. Then each metric should be validated empirically in a wide variety of contexts before being even given or published. For example, we can do empirical validation through experiments, case studies, surveys. We can use proper mathematical modeling, mathematical concepts to formally validate these metrics. But before being published or making decision, we need to do it. In the measurement principle, it is very important to understand that the formulation, characterization and validation, these are critical. But a measurement process always is driven by collection and analysis. If we can collect the data properly and we can analyze the data properly, the numbers properly, the scene properly, scenario properly. So Roche suggests whenever it is possible, the data collection and analysis should be automated, because nowadays we have huge data. Okay, the data is going exponentially, the content volume wise. So we have to be very sure about the automation. The next thing is we need to use, or some valid statistical techniques should be applied, because a product can have an internal attributes, it can have some external attributes, quality attribute. So in order to establish a relationship between the internal and an external quality attributes, we have to use some valid statistical techniques. For example, see, if we have a software, the architecture is overall structure of the software, the architecture complexity. Now, does this architectural complexity relates with the number of defects reported in production use? When the complexity is higher, defects are higher, complexity is lower, defect is lower. So we need to apply and validate using this statistical technique in order to say that we are doing proper measurement. Along with this, with each metrics, we need to have certain interpretation guideline, certain recommendation that this metric will do this thing, this metric will give you this indication. Goal-oriented software measurement. The name is suggesting there need to be a goal. We are calling it as GQM. G is for goal. On the basis of goal, there will be certain questions. And on the basis of these questions, the answer will tell you the metric. So this GQM paradigm was developed by Vasily and others for identifying the meaningful metrics for software processes. For software processes, what will be a proper way for this software measurement? Now, this GQM is emphasizing on what is your goal, what is your explicit measurement goal that is specific to a process activity or a product characteristic. Then we will try to define certain question, and that question need to be answered, because these are to be answered in order to achieve the goal, measurement goal. And then we will identify well formulated metrics that will answer this question being formulated with respect to the measurement goal. And then we'll make a goal definition template, and that will be used to define each measurement goal. So I'll show you that this goal definition template just now. But before that, let us understand what this means, goal-oriented software. For example, the goal is effectiveness of a new programming tool. We would like to evaluate it. What is the effectiveness? Okay. So it can be we were using some C and C++, now Python has come. Now we would like to understand how this Python is going to work in this scenario. Now the first question can come is, who is using this tool X? It can be Python. Now the question can be, say 100 coders are there, 100 people are there. 20 of them are coders, 100 of them, 20 are coders. Now experience of the coders, some of them may have 5 years of experience, some of them may have say 3 years of experience. And you can say that the people who are not coding also, they can also have experience, right? So this is the metric. Metric is coming from proportion of coders, the experience of coders. Let me take one more question. What is coder productivity? If you want to use this tool, what will be the code size? How many line of codes a coder can write? 100 or 1000 or say 10 only? What are the function points? We'll discuss about that. Just understand it is functions, procedures or methods. The next question can be, what is code quality? If someone is writing in Python, how many defects will be produced? What effort has to be put in? This is how the metrics will come from the question being answered with respect to the goal which has been decided. See here, this is the goal. So at the conceptual level, measurement goals involve product, processes or resources. These are the goal. Then coming to the question, at the operational levels, question try to characterize the object of measurement in the context of a qualified issue from a particular viewpoint. These all questions are going to fulfill the goal. And what is the answer? These are metrics. So these are at quantitative level. These are associated with every question. This is a set of data, either subjective or objective, that help us to give a number, a quantitative number. Okay. So this is GQM or goal question metric, GQM. I told you that we'll make a template, and that template will give you the actual scenario. If you remember, this is a safe home product which is employing a software. Now the GQM, when we apply here, the template will answer like this. Let me tell you the template first. Analyze, inside which we are going to give the name of the activity or the attribute to be measured. For the purpose of, inside this what we will give? The overall objective of the analysis. Then we have with respect to, what we are going to write here? The aspect of the activity or attribute that is being considered. Analyze for the purpose of, with respect to, and then we'll write from the viewpoint of, what we are going to write here? the people, the stakeholder who have interest in this kind of measurement. Then in the context of, that is the environment in which the measurement has to be done or measurement takes place. So this is the template, and for every question we are going to fill it. So let us fill it and see what we can do, because we have to start with the question. The template will be fulfilled. For example, the template for safe home will be like this. We need to analyze what? The safe home software architecture. For that we need certain metrics. So the software architecture is the overall structure of the software. Like how are the components, how they are interfaced. What will be the second one? For the purpose of what? We need to evaluate the architectural components, because we have to answer the overall objective of the analysis. Because the name of the activity or attribute to be measured is software architecture, and purpose is evaluation of architectural components. And what is with respect to? We need to write the aspect of the activity that is to be considered. So with respect to, here we will write the ability to make safe home software or the product more extensible. From the viewpoint of who is having interest? The software engineers who are performing this work, who are going to do this extension. In the context of the environment in which measurement has to be taken, so product enhancement over the say next 3 years or 5 years. So this is how we make a template and fill it. With a measurement goal, when we are explicitly or specifically define the goal, as we shown you certain questions in the example also, and this helps the software team to determine certain fact whether the measurement goal has been achieved. Because the goal is defining the question, the question is defining the metrics, and vice versa. For example, the question is, are architectural components characterized in a manner that compartmentalizes function and related data? That is, if you have a component, say you have a class or simple module, do we have the function and data which are related so that we can compartmentalize, we can modularize it? Okay, these architectural components, are they like that? So they are modular so that we can be extending it. The second question can be, is the complexity of each of these component or the module within bounds that will facilitate modification and extension? Is there any problem in modification? Can it be modified or extended? Or do we have some, say, roadblocks in doing that? So these are the questions which are being asked. And depending upon this question, because the goal is very much defined, the answer should be quantitative. It needs to give a number. That is why we are calling about metrics. So metrics that provide an indication of cohesion of an architectural component might be a very good answer for your Q1. That is what is the cohesion? Cohesion is if a module or a component does the like-minded activity or just work what it is being designed for. This is the answer we can give. So I already explained you the example which is above. Function point analysis or function based metrics. Now you see here Mr. Allen, he developed this function point analysis in 1979 at IBM, and this was further modified by International Function Points Users Group. Now this FPA is employed to make estimate of the software project, including its testing in terms of functionality or the function size of the software product. So the cost, schedule and effort can be computed. As I said, this function point analysis may be used for the test estimation of the product also. So this function point analysis, this is going to give you a solution about the size of the solution. It can give you the cost, the schedule, the effort which is employed, which has to be employed. And the important part is it is independent of any kind of programming language. It is independent of any programming language. So it helps in estimation of testing projects also. And since you have all these numbers, now you can have a better idea to discuss it with your, say, stakeholders. Now there are different parts you see here, and you'll be able to understand in a short while how does this function based metric or function point analysis work. These are the 5 measurement parameter which we also called as the information domain values. These all 5 things we need, the amount of them in your product. For example, this is just an example of all these 5 values, and these numbers are already empirically computed. For a low kind of product, or the effort wise or other parameter wise, if it is low, you will use 3, 4, 3, 7, 5. If it is high, 6, 7, 6, 15, 10. Now I'll tell you how these numbers are computed, and then if you just want to do it for low or average or high, you just have to multiply these 2 rows. First, the counts you are going to give, and the row, any of these 3, low, average, high. So what are these first? Information domain values, measurement parameter. First is the application, and user is interacting with the application, and there can be some external data source. So the number of external inputs, these are each external input originates from the user or it is transmitted from another application. Inputs, they're often used to update the ILF, which are inside here, internal logical files. Now coming to EO, this is another parameter. Each external output is derived data that provides information to the user. So user will get the information. That is the direction you see. So what can it be? It can be a report, it can be a screen, it can be error messages. If you have 10 error messages, you'll only compute 1 or just number 1. Number of external inquiries, EQs. Now this number of external inquiry is the input which gives you a software response as an output, which is actually coming from the ILF. What is ILF? Number of internal logical files. So each internal logical file, this is a logical grouping of data that resides within the boundary, resides within the application boundary and is maintained via the external inputs. So these are internal logical files. What are external interface files or EIFs? Each external interface file is a logical grouping of data that resides external to the application, but provides data that may be of use to the application. So you have an application, input are coming from the user, there is external data source. So now we will assign a complexity value to each count. That is, you have certain value of these. For example, you have how many external inputs? I'm just giving you an idea. Okay. Because we'll take an example and you'll see what numbers are we infer. Say external input EIs are 1, EOs are 2, EQs are 2, ILFs 1, EIFs 1. So now this is first column. Now you say I have to compute regarding my functionality point as simple or average or complex. So if you want to compute it as average, you don't have to worry about the first and third row. So 4 into 1, 2 into 5, 2 into 4. I'm multiplying the first with the average row. Then 1 into 7 is 7. Now we are going to add them up, summing. So when we add this, 10 and 10 is 20, 8 and 7 is 15, 15 plus 20 is 35, 35 plus 4 is 34. 35, 39 I guess. Anyways, this number doesn't count. We'll take a proper example. So what we are going to do here is, if this number is 34 or 39, eventually it will be some number, and that we'll call as count total. This number 34 or 39, whichever number is there, the count total. And then we'll multiply it with 0.65 plus 0.01 into sigma fi. Now count total is computed. What is sigma fi? The sigma fi will be computed like this. Sigma fi will be, see, we have 14 parameters here or 15 general system characteristics. So these are value adjustment factor VAF based on the responses to these questions. For example, data communication is required, reusability is required, online data is required. But what is the, say, complexity? That is, we'll give number from 0 to 5. 0, that means we don't require it. It has no influence. But 5, yes, it is very important. 0 means not important. 5 is absolutely essential. So any number between 0 and 5 can be assigned to all these 14. For example, data communication is very important. 5. Online update not required. 0. Reusability somewhat, so gave 1. So we gave all these 14 values some value between 0 and 5. And then all values you have to add. The number between 0 to 5 you have given, you have to add them. So when you add them, what do you get? This is sigma fi, whichever number comes. As I said, 34, 39, or this is sigma fi, whichever number it comes. And you just put it here, that will be the functional point. In the function-based metrics, this is an example. We want to use the function point metric. And this is a simple flow diagram for a user interaction function in, say, a safety, security, safe home system. So there is a hardware whether you are going to key in, and there will be a software inside it. So the function manages user interaction. What is the user interaction? For example, accepting a user password in order to activate or deactivate the system. This allows inquiries on the status of the security zones and the various security sensors, whether they are working, not, my parking is safe or not, whether my kitchen sensor is working, and then display of some prompting messages, also sending some appropriate control signal to various components of the security system. So these are the function managing the user interaction. But our idea is to compute the function point. So what are the 3 external inputs? We need to find out EIs. What are EIs, external inputs? So what are the inputs? Password is an input. The panic button is an input, external input, and the activate and deactivate is the external input. So how many are there? 3. So in front of external inputs, we are going to put under count 3. 3. Okay. How this 3 has come? Now we have 2 external inquiries. What are these? The zone inquiry, which area we are talking about, and which sensor we are talking about. So sensor inquiry. These are 2 external inquiries. So in place of EI, we are going to give the 2 number. Then ILF. How many ILFs are there? System configuration file. So we have 1 ILF. So let us give ILF as 1. 2 external outputs are there. So these are messages which are going outside and sensor status. So these are 2 external outputs being given. So we'll put external outputs as 2. Now what are EIFs? The external interface files. For example, your test sensor, zone setting, activate, deactivate, whether it is not done or not, what is the test status, and the alarm alert. These are external interface files. So we'll put 4 here. Now we have a count for each of these input parameters. Now we need count total. So let us assume that it is simple. We are putting the weighing factor for simple, and these numbers are empirically already found, and these are specific to certain application. So average, complex, these are already empirically predetermined value. So we are not taking average and complex right now. We are just saying that, okay, let us use it for a simple functionality. Okay, so we will not use the last 2 columns. Now we have to multiply the first 2 columns one by one. 3 into 3 is 9, 2 into 4 is 8, 2 into 3 is 6, 1 into 7 is 7, 4 into 5 is 20. Now we'll add them. Summation 50. 50 is our count total. This is our count total. Okay. We need to go for sigma fi. So let us say that it is 46 for a moderately complex product. But I need to tell you how this sigma fi has come. So these are all the general system characteristics. Now you have to give a value from 0 to 5 depending upon the importance of these system characteristics in your software or a product in terms of usability. For example, data communication you give 2, online data entry give 4, 5, reusability 0. So every number you have to give between 0 and 5 and just add them. And just assume that that number is 46. You can try with any other number, 40, 50, it will be below 70. Okay. So now this addition of these numbers, each number between 0 to 5 assigned to these 14 system characteristic. You add them, and I'm just saying that it is 46 to make our computation easy. So this is 50. This is how much? This is 46 by adding all these. And then the final computation, 50 is the total count, 46 is the sigma fi, and the actual functional point is 56. 56. Now the thing is, why it is important? What do we infer from it? Our idea is not for computation. What do we do? So based on the projected this function point value, which is derived from the requirement model, now the project team can estimate the overall implemented size of the safe home user interaction function. Just assume that past history of this kind of project has given us that one function point translate into 60 line of code if we use the object-oriented language. So how many function points are here? 56. And one function point gives 60 lines of code. So 60 into 56, this will be the number of line of code. So this is the line of code estimation. For example, 12 function points are produced for each person month of effort. So effort is known, 12 FPs. What will be 56? How many person month? So just divide 56 by 12. This is, you will get the answer for the effort. So line of code you got, the effort you got. Now just assume that the past project, it was found that the average of 3 errors per function is found during the requirement and design review. So for each function point, there are 3. So you can assume there are 56 function point. There are 4 error per function point during unit and integration. So 4 you are getting, so 56 are here, 56 into 4. So you know about the number of errors per function point, and function point is known. So the line of code is known, effort is known, number of errors are known. So this kind of data help you assess the completeness of a review also the testing activities. Okay, how much code you have written, what effort you have to put, and the review and testing activities. That is why this function based matrix is so important. Let us take one more example of a function point analysis. Now we have to compute the function point productivity, documentation, cost per function of this data. The data, the first 5 is basically the input parameters, the information domain, 24, 46, 8, 4, 2. This we are going to take as the input domain. Then the effort is given 36.9% month, technical documents are 265 pages, user document 122 pages, and cost is $7,744 per month. Now various processing complexity factors are also given. Now you see these are the complexity factors already given. So there are 14 complexity factors between 0 and 5. This is already given to us. So number of external inputs, EI, is because user input is external input. So what is the number? 24. What is the number of external outputs, which is the user output? So we are going to put 46 here. Number of external inquiries, which is the number of inquiries, we are going to put 8. Number of internal files, which is number of files, which is going to be 4. Number of external interfaces, EI, what it will be? This will be number of external interfaces 2. Now let us assume, for example, this is a pre-made empirical values. I'm not going to use it. I'm just saying that for this particular product, this particular project, the numbers for say the average values are 4, 4, 6, 10, 5. I've just changed the numbers. This is for average. This box is just for example. I'm saying for this particular project, the numbers have changed. So 4, 4, 6, 10, 5. So what we'll do? 2 into 4, 96, 46 into 4, 184, 8 into 6, 48, 4 into 8, 40, 2 into 5 is 10. So these values have come. Now we are going to add them. And this is going to be count total, 378. And now we need to find sigma fi also. So count total is known. How do we know sigma fi? Because already the values are given. We don't have to give the number from 1 to 14. Otherwise we would have given 0 to 5 ordinals value to each of these 14 values, and then we would have just added them. So these are all values 4, 1, 5 like this given, already given in the question. So we'll just add them. So when we add them, we get 43. So don't go into the computation detail, just know how we do it. 43 is there. Count total is 378. Then we know the formula 0.65 plus 0.1 into sigma fi. Sigma fi is simply 43. Now 378 here, just put it, you get 408. Now this is the function points. Now you have to compute the productivity. What is the productivity? Productivity is simply the function point divided by the effort. Function point is 408. Effort is 36.9 person month. Divide them. What do you get? 11.1. So this is the 11.1 value is productivity. Then the documentation. For that we have to add the technical document as well as the user document. So you have 265 plus 122. Just add them. These are going to be the number of pages. And what is the documentation? The number of pages of the documentation divided by the function point. So what do you get? Just divide them. 387 by 408. This is going to be 0.94. So this is 0.94 for documentation. Now coming to the cost per function. And this is simply computed by cost divided by the productivity. So the cost total given is 7,744 per month and divided by the productivity 11.1, which we already computed. That already first thing we computed. So that will be $700. This is how we compute the function matrix. Matrix for specification quality. Now Davis and his colleagues, they propose characteristics that can be used to assess the quality of the requirement model, because the first thing is to gain the requirement. In terms of requirement model, we finally make the corresponding SRS, software requirement specification, or the requirement specification. Now we are interested in the matrix for this specification and what is the quality of this specification. For example, this SRS, what amount of all these or degree all these have? Specificity, lack of ambiguity, whether it is complete or not, correctness, understandability, verifiability, internal and external consistency of the document, the achievability, whether we can achieve these requirements or not, concision, the traceability, the modifiability. Traceability is that when you complete the project, can you trace back? Modifiability, can you change? Precision, how accurate, precise it is. Reusability. Okay. Along with this, the Mr. Davis and others, they also said that these high quality specifications are electronically stored. How? Whether they are able to execute, or if you are not able to execute because the specification requirement model may not be executable, they are at least interpretable only. And the annotation should be given wherever it is admissible. And the document or the SRS should be, or the model should be stable, versioned, organized, cross-referenced. These are very important. And specified at the right level of detail, this documentation or the product specification. So many of these characteristics, they seem to be very qualitative. From say accuracy we can compute, but what about the usability or the ambiguity? How do we check? So we will use the matrix. We assume that this is, for example, you have SRS, software requirement specification. The N sub R is the requirements in specification. So what is the NR? NR will be NF plus NNF. All these F and NF, these are subscript. So this first one is the functional requirement. The second one is the non-functional requirement. Non-functional requirement are specifically written, and non-functional requirement are some are explicit, some are implicit. Now this is a value, but in order to find out, says a specific SRS function or value or metric, specificity, two people may understand the same requirement in different way. They may interpret the same requirement in different way. This may be possible. So how do we go about it? We have another metric, which is N by N. First is NUI, which is the number of requirement for which all reviewers, they have identical interpretation. That is, you and me both are interpreting the requirement in the same way. So NUI by NR. This is the number of requirement. All have same interpretation. And NR, you already know, NF plus NNF. So closer the value of this Q1, if it is 1, closer to 1, then the ambiguity in this specification is less. So this is how the metric can be computed. For example, you need to compute the completeness of functional requirement. There are functional requirement, non-functional requirement. So we have functional requirement and we need to know the completeness. For that we have this matrix nu by ni into ns. Nu is the number of unique function requirements. All the function requirement, no duplication, unique function requirement should be there. It should not match with others. Ni is the number of inputs defined and implied by the specification. In the specification of function or how many inputs it's going to take. So these are the inputs ni. Ns is how many states it will change. So number of states specified for this function. You can see it in the state diagram also. Okay, this is the completeness. So you get a matrix for completeness of functional requirement of the specification. Now Q2 will measure the percentage of necessary function that have been specified for a system. So this value will tell you, okay, these are the functions which need to be defined or they are specified in the function. These are the necessary function. But the one point about this metric is it does not address the non-functional requirement. In order to get that, in order to incorporate it into overall metric for completeness, functional and non-functional, then we need to validate the degree to which the requirements have been validated. For that, another matrix is there, Q3, NC by NC plus NV. Now NC is the number of requirements that have been validated. And we are saying that these are correct. That is why we have NC. They are validated and they are correct. This is NC. What about NV? These are the number of requirements that have not yet been validated. So this is the Q3 which is taking the overall completeness matrix. This is how we measure the specification quality. Architectural design matrix. So we want to find out some numbers, some quantitative measure, so that we can understand what is the present state of architecture or the design. So architectural design matrix, they focuses on characteristics of the program architecture, emphasizing on architectural structures and effectiveness of modules or components. You know that the architecture is what? The overall structure of the software. And design is that total conversion of requirement so that it can be converted to the actual code. So now these things need some numbers, whether we have made a good architectural design or not. So these metrics which we are going to discuss, they are black box. We don't go into the detail or we don't have any knowledge of the inner working. Cord and Glass, they define 3 software design complexity measures. What are these measures? These are pertaining to your architectural design. So the first one is structural complexity, then the data complexity and the system complexity. Complexity, we have already talked about cyclomatic complexity. So this kind of complexity or this kind of measures or metrics can also be talked about in here. So here we have a call and return architecture. That is the main module or main function will going to call certain function. Those functions are going to call again some functions. So these are a kind of call and return architecture. This is a hierarchical architecture. We have a proper hierarchy here. Okay. Now for this hierarchical structure, if we want to define these different complexities with respect to the architectural design matrix, the structural complexity of a module I, module can be a combination of functions. So this is defined as what? It's simply the square of fan out. For that module or that group of function or a separate function, just square the fan out. Now the question will be, what is the fan out? See, the fan out is the number of submodules this is going to invoke. For example, here there is a component. Now here we have different functions calling this component or this function. This is called fan in. That is, fan in is this function is invoked by others. But fan out is how many components or the modules or the function this component is going to invoke. Okay. So usually we want high fan in and low fan out. We don't want low fan in and high fan out. So fan out is that a module or a component, how many it is going to invoke. So this is the fan out. So just square it, you are going to get the structural complexity. Now coming to the data complexity. The data complexity is the complexity in the internal interface for a module I. How do we define it? What is the interface? How do you get inside a function or a module? Through variables. And what do you get from these functions or the modules? Variables. So we are talking about the number of input and output variables that are passed to and from this module. Vi divided by fan out plus 1. Fan out we know number of modules or functions this module is going to invoke. But Vi or V is the number of input and output. For example, let me make a function. Assume that it takes 4 variables as input and it is returning, or say through pointer or by any other mean, it is returning say 2 variables. So number of Vi is the number of input and output variables. So in all we have 6. So that is what you are going to put it here. Fan out is number of modules this module is going to invoke. Coming to system complexity in the architectural design matrix, just add the structural complexity with the data complexity. This is the system complexity, because we already talked about the fan out and input output. So all these complexity, the question is, the word complex is complex. So the complexity value, if it increases, the overall architecture complexity will increase, and thereby the effort in integration and testing of these modules will increase. Now Fenton, he suggested a variety of simple morphology that is based on the shape. Morph is shape or face. So simple morphology matrix in order to compare various program architecture and using very straightforward dimensions. What are these dimensions? If we take call and return architecture, that is a main function calling a function, then that function is calling another function, likewise. So call and return architecture, if we take, the simple straightforward dimension is when you make this graph or this figure, the simple way to find out the size will be n plus a. What is n here? N are these blocks, which are the number of nodes in this graph, and a is the number of arcs. These are the number of arcs. So n plus a, nodes plus arc, is going to give you size. So when you add them, if you consider these nodes, there are 17 nodes. How many arcs are there? There are 18 arcs. Add them. And what are you going to get? 35. So size you got. There are other parameters also, like the depth and the width. So depth is the longest path from the root, which is the top node, to a leaf node. So in the figure, if you see what is the depth, you can just see how many levels it has. 1, 2, 3, 4. So depth is the number of levels you can assume. So this is the longest path from the root to the leaf. So the answer here is 4. Depth is going to be 4. What about the width? Depth is from top to bottom. That is how we got 4, the depth. And the width. Width is the maximum number of nodes at any one level of architecture. That is, we have 4 levels, which is of course our depth also. And width is what? The maximum number of nodes at any level of architecture. So you just compute this highest number of these boxes. In which level they are? In the second there are 6. In the last one also we have 6. So width is 6. So arc to node ratio, arc can be computed as A divided by N. Number of arcs divided by number of nodes. What do you get? You have the numbers. So this value will give you the idea about the coupling of the architecture. So this R equals A by N measures the connectivity density of the architecture, and it is giving you an indication of the coupling of the architecture. So 18 by 17 is going to be 1.06, and that is the metric. We are going to talk about DSQI. This is a Design Structure Quality Index. So this the value will range from 0 to 1. Now what is this DSQI? This is about architectural design matrix. This is about design. This is about architecture. So this is a proper matrix which will give us a number. So using the concept which were similar in the IEEE Standard 982.1 2005, the United States Air Force System Command, they use this information obtained from the data and the architectural design in order to derive this DSQI, Design Structure Quality Index, which varies from 0 to 1. So how do we compute it? Before that, there are certain AF Design Structure Quality Index. There will be 7 of them. S1 is the total number of modules. S2 will be number of modules dependent upon correct data sources or produces data used. S3 will be modules which are dependent upon the prior processing. So S4 will be the total number of database items, and S5 will be the total number of unique database items. S6 will be the number of database segments, like the record. If you make a table, one table in a database, number of records and individual objects. S7 will be those number of modules with single entry and exit. So this S1 till S7 will give numbers, and then we will compute the DSQI. How do we compute it? Before that, we have to compute D1 to D6. What is this D1 to D6? So D1 is the program structure. How do you define it? As I said, D1 to D6. This D1 is if the architectural design was developed using certain distinct method. If you have applied, or the software or the program or the architectural design was made using certain special distinct method, like the data flow oriented design or the object oriented design, then D1 will be 1. Otherwise, we'll put D1 as 0. So this is a specific value. It can be 0 and 1. This is the D1. As I said, we have to go from D1 to D6. What is D2? 1 minus S2 by S1. I told you all S1 till S7 you have to give numbers. So 1 minus S2 by S1 is module independence. Then modules not dependent on prior processing. So D3 equals 1 minus S3 by S1. So basically probability it is going. It's all probability things. So S3 by S1. Then the database size S5 by S4. You compute it and then subtract it from 1. You get the database size. Then the database compartmentalization, modularization, D5. So S6 by S4 and subtract it from 1. Module entrance or exit characteristic. This is S7 by S1 compute, subtract it from 1. So D1 till D6, this is how we get. So we have to give numbers to S1 to S7. These D1 to D6 can be easily computed. And DSQI will be simply WD. I is the subscript. That is, you have to do W1 D1, W2 D2 like this. Now you'll ask, what is W? W is simply the weight given to all these D's. This is a relative way. If you say that something is important, you say module interdependence is very important. So you will give a weight. Database size is important, you will get a weight. If a module entrance exit is not very important, you will get a lesser weight. So this sigma wi should be 1. Okay. Now this weight you have to be along, it should add to 1. If all these di's are equal weighing, then you will get this wi will be 0.167. So the value of DSQI what you got will be compared to the past design. So if the DSQI value is lower than the average what you have got earlier, it indicates that you need to work on your review and design work. Metrics for object-oriented design. Now, object-oriented design has a lot of concepts. We start with the creation of class, then we create objects, then we have functions inside and attributes which are encapsulated. Then we have these messages, passing through classes. Then there is inheritance going on. There is polymorphism. So Whitmire, he describes 9 very distinct and measurable characteristics of an object-oriented design. So size is a static count of these object-oriented entities like the classes or the operation or the inheritance tree, depth of the inherent tree combined with this, the size. So what I'm trying to suggest here is that there are certain distinct characteristics, and those characteristics can be an idea of matrix for the object-oriented design what Whitmire has suggested. For example, complexity. Complexity is all about how classes of an object-oriented design, they are interrelated to one another. So we'll talk about the interrelation here. Coupling is the measure we measure it by counting physical connections between elements of the object-oriented design. For example, the number of collaboration between classes or the number of messages being passed between objects. Sufficiency is the degree to which an abstraction possesses the feature required by this abstraction or a class. This is one more characteristic. Completeness. It will determine whether a class fully delivers the set of property for which it was being designed or written. This is completeness. Cohesion is whether all operations work together to achieve a single like-minded, well-defined purpose. This is cohesion. Then primitiveness. This is the degree to which an operation is atomic. What does it mean, atomic? That is, the operation cannot be constructed out of a sequence of other operations contained within a class. So, if certain operations are there, this operation cannot be completed, cannot be concluded until those operations are also being taken care or included. This is the primitiveness. So, if you have a sequence, that sequence will be followed. That is what we mean, the operation has to be atomic. Similarity means this will determine the degree to which two or more classes are similar in terms of their structure, function, behavior, and purpose. This is similarity. Volatility. Volatility, it measures the likelihood that a change or a modification will occur. So all these are measurable characteristics, and the product metrics for the object-oriented system can be applied to the requirement model also. So these are certain ways to understand the object-oriented design. The CK matrix suite, and this is class-oriented matrix. In an object-oriented design, the class is the fundamental unit of an object-oriented system. Because when we make a class, then we'll make objects. A class is encapsulating or containing what? Data or attribute. And then we have function. The function are going to manipulate this data or work on this data. This can be operation, this can be function, this can be procedure. So a class will encapsulate these. There can be a parent class from where the subclasses can be inherited. So inheritance means taking the attributes and operation as it is. So there can be another class which can be a subclass of a superclass or the parent. And these all collaborate with one another. So these characteristics, this can be used as the basis for measurement and metrics. So Chidambar and Kammerer, they have proposed a CK. C is coming from Chidambar and K is coming from Kammerer. They have proposed CK object-oriented software matrix suite. So we'll see 6 class-based design matrix for object-oriented systems. We'll see one by one what they are saying, because there are 6 different in this suite. Weighted methods per class, WMC. Now what does it mean? Just assume that we have a class C and we have, say, n methods in this class. And this n methods have complexity C1, C2 till Cn. So a class we have defined have certain functions and each of them have corresponding this complexity. Now this complexity can be any complexity. For example, you assume it to be cyclomatic complexity. You know how to compute cyclomatic complexity. Basis path testing, I told you, the independent path we find out. E minus n plus 2 and number of regions and the predicate nodes plus 1. So cyclomatic complexity, you can also use Hellstedt's complexity matrix. But you need to normalize so that the nominal complexity for a method takes on a value of 1.0. So you just have to add these complexities. Just add the complexity. This is the weighted methods per class. So the number of methods and their complexity, these are the indicators of the amount of effort required to implement and test a class. So this is a clear indicator, WMC, that how much effort you are going to put and how much effort in testing also. If you have large number of methods, more complex is the inheritance tree, because all the subclasses are going to inherit the method of their parents. This can happen. More method, if they are very application specific, software specific, work specific, you may not be able to use or reuse it again. So limiting the potential reuse. Therefore, WMC should be kept as low as possible, as low as reasonable. In CK suite, we have depth of inheritance tree, DIT. So inheritance is a class properties are inherited by another class. For example, you have the attributes and function of class A, class B you have defined, class C you have defined, and you have inherited the classes which are above it. So one is called parent, the other is called children like that. But the depth of inheritance tree is how far you are going to down the level. So this metric is the maximum length from node to the root of the tree. How many nodes you are covering? For example, 1, 2, 3, 4. Okay. Just compute the number of nodes. You have 4 nodes here. So this is the depth of inheritance. And since we have these C1, for example, C2, just take. The DIT of class hierarchy in this figure, as I am suggesting, it is 4. And when this depth of inheritance increases and when it decreases, that directly represents the complexity of object-oriented design. As DIT will grow, the lower level classes are bound to inherit many methods from C, C2, C21, C211 will inherit. Okay. Now DIT I am showing because here you see the bottom is quite heavy. DIT2, the balance tree, if you see here. So we want the balance kind of tree. because we want that the inheritance should be up to a limit, should be controllable. So the depth of inheritance tree DIT should not be higher than what we are expecting. So difficulty we will have in order to predict the behavior of the class which are in the lower depth in the inheritance tree. So a deep class hierarchy, clearly you see it means that the design complexity of your design is quite higher. Large DIT values, it implies many methods can be reused, because the C method has been reused to C2, C2 has been reused to C21, C21 is reused to C211. So reuse can be a thing here. Next thing comes is number of children. Number of children is the subclasses immediately subordinate to a class. These are termed its children, and this is the number of children. For example, here you have, this is a C2 class. Now it has subordinate, immediate subordinate classes as C21, C22 and C23. So how many number of children it has? 3. As the number of children will grow, of course the reuse will increase. But as the number of children will increase, and if you have an abstract class, if a parent class is abstract class, the abstraction of, say, phenomena will be diluted if some of the children are not appropriate members of the parent class. So these are we need a proper balance of this number of children, because though reuse is increasing, but the appropriate implementation should be there. As the number of children will increase, the amount of testing will also increase. Coupling between object classes. This is CBO. This is CK suite, one more metric. CBO. Coupling between object classes. Now when you make a class, when we make the, or say the components, subcomponents on the modules, they are going to somewhat couple. So the CRC model may be used to determine the coupling between object classes, and this you can take from CRC index card. So CBO is number of collaboration which are listed in the class as is in CRC index cards. You see here, this is the collaborators, these are the collaborating classes. So all this we can get it from CRC index card. As this CBO will increase, the reusability of class will decrease. High value of CBO means what? Because there is so many collaborating classes and coupling is there, so modification will be complicated and testing will be. So CBO values for each class should be kept as low as possible, as low as reasonable. Either you take the conventional or any, coupling has to be as low as possible. CBO is coupling between object classes. If you see here example also, I tried to show you how many CBOs this A, B, C, D have. Response for a class, RFC. Now RFC is what? First of all, let us understand. Methods that can potentially be executed in response to a message received by an object of that class. Now you are receiving a message and say M1 is an object of this class. Now the invocation of R1 has happened. That is, RFC measures the immediate surrounding of a class. If some message is coming and some other, say, object are being invoked or some other thing are invoked, this is the response for a class. So we say it in the size of the response set, we take the union of the which is in getting message and what are invoked. So RFC is the number of method in this response set. So as this RFC will increase, the effort of testing also will increase, because the test sequence will grow, because some input is coming here, other is getting invoked or called. So as the RFC will increase, the overall design complexity of the class will also bound to be increased, like R1, R4, R3, they will also get invoked. Lack of cohesion in methods, LCOM. Now LCOM measures the dissimilarity of method in a class by instance variables or attributes. There are different variants. Let me take an example of a class. Now we want that cohesion should be there inside a class. Now each method in a class are bound to access one or more attributes. These are called instance variable. So when the method is making use or manipulating or accessing one or more attributes, LCOM is actually defined, which is the number of methods that access one or more of the same attribute. Please understand, number of methods that are accessing one or more of the same attribute. For example, here variable ABCD is given. The method 1 is accessing A and C. The method 2 is accessing B. The method 3 is accessing A, B and D. This is what I am talking about. Number of methods that access one or more of the same attribute, LCOM. So normally we talk about cohesion, but here we are talking about lack of cohesion. If no method access the same attribute, you are bound to have LCOM value as 0. No one is accessing the same one. In order to illustrate, to understand the case where LCOM not equals 0, you just consider 6 methods. 4 of the method access one or more attributes in common. So what do we say? We say LCOM is equal to 4. The lack of cohesion in methods is 4. So this is how the LCOM works. If LCOM is high, the complexity of the class design is higher. Oriented metrics. The mood metrics or mood metrics suite. Now this MOOD stands for Metrics for Object Oriented Design. So we will get the number, the quantitative measure for the design, and this is suite. That is, this is not one metric. The first metric is method hiding factor. The second one is attribute hiding factor. Third one is method inheritance factor. Fourth is attribute inheritance factor. Then we have the coupling factor, and finally the polymorphism factor. So 2 of them we are going to see. Now Harrison, Council and Nithi, they proposed metrics that provide a quantitative indicators for object-oriented design characteristics. That is, we are going to get the numbers, and numbers we can very well estimate. So a sampling of this mood matrix, let us take the method inheritance factor. This one we will take, and we will take the coupling factor. So method inheritance factor, here it is all about inheritance and method. In class based, in object oriented paradigm, we are talking about methods which is inside the class, and inheritance is how the attributes and operations are inherited by a different class. So degree to which the class architecture of an object oriented system makes use of inheritance for methods, which we also called as operation, an attribute is defined as. How do we define this MIF? We define this MIF by this expression. This is the summation of MICI, this I, all I are the subscript, divided by sigma MACI. Now this summation, sigma will start from somewhere and it will end to somewhere. So sigma will start from 1 till TC. What is TC? Total number of classes. So TC is defined as the total number of classes in the overall structure, which is the architecture of the software, that is the design. Okay. Now this CI, what you see here, is a class in this architecture. So this MACI, which is the denominator, how do we define it? And even the numerator also will see. Actually, the denominator is MDCI plus MICI. This MA, MD and MI. This is also class. C is the class we are referring to because there are different classes. So MA is number of methods that can be invoked in association with this class. So we are talking about association with CI. MD is the number of methods declared in the class, and MI is the number of methods inherited, not overridden in the class. Let me show you what is this inheritance and overriding. See, this animal class is there and it has some attributes and say functions. Now dog is extending or inheriting the animal. So all the content has come, data, one, move, eat. So this is inheritance, simple inheritance. But if dog wants to make its own implementation for the function say move, so this move, the function being newly implemented by dog, not use the previous one of animal, this is called the overriding method. So inheritance, of course, it is already there with dog, others. What I'm trying to suggest here is we have a base class, we have a derived class. So all the content of base class will come to the derived class if it is in the public domain. Of course, the private won't come. And other function which are inherited can also be overridden. So these are the values. So the MIF value will tell you, it will indicate the impact of the inheritance, because all these parameters we discussed, it is all about inheritance. In this mood matrix suite, we have coupling factor. The matrix suite has 6 of them. So we are taking one of them, which is coupling factor. This metric coupling factor was proposed by Mood, and this is actually a ratio. But before we go ahead, this is coupling. These are different module or these are different components. There is no coupling at all in the first case. Here there are certain dependencies between the independent modules, but here we have many dependencies. So these 4 are highly coupled and we don't want it. So as I was saying, the ratio of coupling involved between the classes, that is what coupling factor finds out. So the ratio of coupling is evaluated using a fraction. And what is the numerator here? See, just understand the formula. This in the formula, this CF is the coupling factor, sigma I, sigma j. Now sigma is the summation. It will start from I equals 1 till the TC. TC is total number of classes. Total number of classes in your discussion. Now is client. What is this is client? Is client, and in the bracket we have CI comma CJ. Is client. CI CJ. So there are 2 different classes. Now this whole result will be 1. It will be 1 or 0. So it will be 1 if and only if a relationship exists between the client class and the server class. Client server classes are not equal. If one is a client of other, it will be 1. If it is not a client, if there is no relationship between the client class and the server class, then we say it will be 0. So the numerator can only be 0 or 1. So the ratio of coupling is evaluated using a fraction. Here you see the numerator. It is representing the total number of non-inheritance couplings in the module. Okay. And what are you getting in the denominator? The denominator signifies the maximum number of coupling that is possible for the corresponding module. TC square minus TC, which is the square of the total number of classes and subtraction with total number of classes. Okay. So this is how we find out the mood metric coupling. So this is all about how much different modules or classes, they are coupled, or the functions inside the classes or the modules, they are interconnected. So as the value of this coupling factor will increase, the complexity of the object-oriented software will automatically increase. But the understandability, the maintainability, and the potential for reuse, it will decrease. It may suffer. So we need coupling as least as possible. Object-oriented matrix proposed by Lawrence and Kidd. Okay. Now Lawrence and Kidd, they divided the class-based matrix, object-oriented matrix, into 4 categories, and all have relationship or bearing on component level design. And these 4 categories are size, inheritance, internals, and externals. What is size? The size-oriented matrix for this they proposed by Lawrence and Kidd for an object-oriented design focus on counts of attributes and operation. So this is a class. These are the attributes, and these are the function operating on these attributes. So the counts of attributes and operation for an individual class. This is size-oriented matrix. Inheritance class, inheritance-based matrix. This works on operation which are used through the class hierarchy. That is, one class inherit the other class, then it is actually using or reusing the methods which are defined or implemented in the base class. Then the class internals. This class internal matrix, they are talking about the cohesion and code-oriented issues. So if we are talking about a class, does this class do all the like-minded, single-minded, one-point oriented work? The external matrix is talking about coupling and reuse. Coupling means 2 modules, how much interaction they have. So let us take the example of these metrics which are proposed by Lawrence and Kidd. The first one is the class size. Now the overall size of the class, how can we determine it? We have certain measures. Operation, the total number of operation. It can either be inherited or it can be private also, encapsulated within a class. That is the functions. Total number of attributes, again both inherited and private, encapsulated by the class. You can say total number of operation and total number of attribute count in the class. So this is the class size. So large values of this class size will indicate that a class may have too much of responsibility, and that is going to reduce the reusability of that class. And when you are going to implement and test, it will be difficult. It will complicate the things. Inherited or the public operations and the attribute should be weighted more heavily in determining the class size. Okay, because mostly the functions or attributes which are inherited in the different base classes, that has to be weighted more. The private operations and attributes, this will enable the specialization. Why? Because it is more specialized. It will not be inherited, it will not be used anywhere else. So they are more localized in the design. So averages of the number of class attributes and operation we can compute, and if you have a low average values of this class size, more likely that classes within the system can be reused. They can be reused in other projects or in this only. Operation oriented matrix. Operation is all about the function, the procedure, whichever way you call it. The operation or the function are working on the attributes in the class which are being encapsulated. So whenever we talk about the object-oriented system, we generally talk about class. Other things we don't talk. So there are metrics which are proposed mostly on the class basis, not about the operations in the class. So Churcher and Shepard, they discuss, for example, just write a function. The method tend to be small, both in terms of number of statement and in logical complexity. This suggests that connectivity structure is more important than the content of modules. So what is inside the module is not that important. The connectivity structure of these methods inside a class and outside the class is more important. However, we can gain insights by examining the average characteristics of a particular method or operation. So there are three simple metrics proposed by Lawrence and Kids. How to examine the average characteristic of methods and the operation present in the class. The first one is average operation size, OS with the subscript average. Now size can be determined how? By counting the total line of code, LOC. For example, this is a function. So we can compute or count the line of code and the number of messages sent by operation. How do we send the message and get the message? Through the function interface. That is the input parameter and the output parameter. So as messages sent by a single operation increases, the responsibility is not being properly allocated within the class. There is only one function is doing a lot of work. The other function are not doing that much of work. Operation complexity, OC. Now the complexity of an operation, this can be computed how? Using any complexity matrix like the cyclomatic complexity. So designers should see and strive to keep this operation complexity as low as possible. And then comes the average number of parameters per operation. So in an operation, in a method, how many parameters are there? The input parameters, the output parameter. Larger the number of operation parameter, I'm talking about this, the more complex the collaboration between objects will be there. So the input parameters, output parameters, they have to be as less as possible. So the MP average should be as least as possible. Metrics for source code. Now the programmer and software team, they are more interested in the software code. Now Halstead, he gave a theory of software science and he was the first to propose the analytical laws for the computer software. So the Halstead, he assigned certain quantitative laws to the development of computer software. From A to Z, he said we can compute it and we can do it using just the primitive measures. Only the code, that is, even if the code is generated or even the design has been completed, we can compute so many things, almost everything, using this Halstead theory. And the basic measure, which is or the basis of Halstead theory or source code matrix, is how many number of operator and operands are there. I'm just writing a very naive code, easy code. And I'm just trying to point out what are the operator and what are the operands. Please remember, operators are all those symbols which are provided by the programming language. And operands are all those which a user has used, he has given, he has defined, he has declared. So if is an operator, braces operator, round bracket operator, angle bracket operator, double quotes operator. Okay, what are the operands? X operand, 5 operand. These are given by S. So we will just count them. This will be N1, number of operator, number of operands, N2, capital N1, capital N2. Now just write them and remove the duplicates. Just count. If you have multiplicity, just count 1. And that will come from N1 only. So N1 will get reduced to small n1 because we have just reduced the multiplicity. Count the operator, remove the duplicity or multiplicity, you will get N2, number of distinct operands that appear in a program. So Halstead used these these parameters to develop expressions for the overall program length, potential minimum volume for an algorithm, the actual volume in terms of bits, the program level, that is the complexity, the language level, which is constant for like COBOL or C or C++ or C Sharp, then development effort, how much effort will be required, what will be the development time, and the projected number of faults, problems in the errors. So he gave these all expressions. So this is the basis. I told you this has come from simple code or the algorithm. So he said the length of the code will be n1 log n1 plus n2 log n2. These are all small logs. Base is 2. Program volume will be capital N. Capital N we have found out. And then log n1 plus n2. This is log base 2. And V, capital V, which is the volume, will vary with the programming language. And this will represent the volume of information in bits. So minimum volume should be there for a particular algorithm. He also said volume ratio, which is actually the one inversion of your difficulty. So this is the ratio of volume of most compact form of program to the volume of the actual program. So if you have a very good program and the actual program, that is the compact program divided by the actual program, this is the volume ratio. L, this is volume ratio, has to be less than 1. This is the volume ratio, 2 by small n1 into small n2 by capital N2, and you just invert it. Just do 1 by L, you will get the difficulty. So this difficulty and volume, when you multiply, you will get the effort. Effort will be V into D. So this is how various parameters. Also, I tried to show you on the right side bottom. There are various ways you can use expression to find out. We'll take the example also. We are taking an example of Halstead's matrix. Various things we can estimate or find out using Halstead matrix. So we have taken an example, very small code. So we have to find out the operators and operands. Every formula is dependent on these values only. Small n1, small n2, capital N1, capital N2. So first of all, what are the operators? Operators are all those symbols or notation which are provided by the programming language. Those which we are giving are called operands. Okay. So we will make a list of operators and then operands. First of all, let us start with the operators. If is the operator, round bracket, then angle bracket, then round bracket close, curly brace, if, round bracket again, angle bracket, then round bracket close, is equal to, then star, that is the multiplication, and semicolon, and the braces. Okay. Now you have to count it. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this is the 13. These are the total number of operators, and that is the capital N1. Okay. Capital N1 is the total number of operators. Let us go to the operators. Operands. Operands are those which are given by us. So K, then 2, then K repeated. Don't worry about repeating. Then we have 3. Then these are constant and variable basically. X, then again X, and then we have K. So these are the number of operands. How many are these? Just count it. They will be 7. So number of operands are 7. N2 is 7. Capital N2 is 7. Now the question will be, what is small n1 and small n2? These are distinct operators and operands. So now just you have to remove the duplicacy or multiplicity. So small n1 will come from this first column. First column we have used. So if is already there. So one I have crossed and other I have just removed because it is repeating. Round bracket also repeating. Angle bracket is not repeating. And then we have a round bracket. This also is repeating. So I am removing one of them. Curly brace. No, all these are distinct, unique. Now you just have to just mark it with a line and just calculate how many lines are there. Okay. We have just removed 3 of them. 3 are the duplicates. So just cross it and just count how many lines are there. These are 10. So 10 is the distinct operators. I have just removed the duplicacy. The same thing we have to do for the operands. Now this k is repeating. This is also repeating. 3x is repeating. Okay. So k repeating. So 1, 2, 3, 4. How many are there? Small n2 is 4. Okay. Now these values will be put, and all the formula, they have these content only, these notations only. Calculation I have already done, so I will tell you what is the logic here. The first thing we will find is the length. Length is capital N. Length is denoted here by capital N, which is equal to capital N1 plus capital N2. So what are the values? We know already 13 and 7. So you just see here N1 plus N2, 13 plus 7 is 20. Now coming to vocabulary. Vocabulary is small n. Vocabulary is small n, and this will be computed by small n1 plus small n2. This will be small n1 plus small n2. So small n1 is 10, small n2 is 4. 10 plus 4 is 14. So this is the computation of vocabulary. Then the estimated length. This is represented by n cap, estimated length, n cap. So this will take some time. N cap will be small n1 log base 2 small n1. So n1 log base 2 n1 plus n2 log again base 2 n2. Okay. Now only thing of concern here is, let me show you the computation. N1 you know it is 10, N2 you know it is 4, but log is base is 2. So we have to convert this log base 2 to log 10. So log base 2, most of the scientific calculator you won't be able to calculate. For that you have to change the log to base 10. For that just change the base 10 and just divide it by 0.3010. So log 10, see the base I have changed and just divided by 0.3010. And log 10 is 1, and log base 10 of 4 is 0.6020. Computed, it will be 41.222. Next thing will be purity ratio. Purity ratio will be this n cap which we have just calculated, estimated length, divided by capital N. N cap was 41.222. And what is the capital N? Capital N is 20. So this is the computation. Purity ratio is, it will be 2.0611. Next thing is program volume, or it is volume. So volume will be capital N log base is 2, and then we have N1 plus N2. These are small n1 and n2. So 20 is capital N, log is base 2, N1 plus N2 we have already computed, it is 14. So as I'm saying that you have to change the log base 2 to log base 10, just divide it by 0.3010, 76.154 will come. Now volume is there, not difficulty. The difficulty will be small n1 by 2 into capital N2 by small n2. Capital N2 by small n2. Okay. Now you see here, n1 is 10, capital N2 is 7, small n2 is 4. So it will be 8.75. Now let me tell you one more thing. Here is one more thing which is called volume ratio, VL. Volume ratio. This is 1 divided by difficulty. Just divide difficulty by 1 and you will get the answer. Effort is simply volume into this difficulty. So 8.75 is the difficulty. Volume we already know, 76.154. The answer will be 666.3475. So this is how we calculate the Halstead matrix. These are all the basic thing is number of operators and operands, and discrete operands you have to find out. Metrics for testing. So the majority of the metrics which we have seen for testing, They focus on the process of testing, what process are being adopted, but not on the actual technical characteristics of the test themselves. So tester has to do what? They have to rely on the analysis, design, the code matrix, for design and execution of the test case. So they have to rely upon all this. So the architectural design metrics provide certain information to us, like architectural design we have already seen. So what are the metrics? What information do they give? They give us information like ease or difficulty for integration testing. Do we need stubs and drivers, like the need for the specialized testing software? Do we need a main dummy program or the sub-module dummy programs? So this architectural design matrix will tell you. Along with this, the architectural design matrix gives certain more things. The cyclomatic complexity also, it will give you how much extensive unit testing you have to do. If you have high cyclomatic complexity, likely the module is error prone. So using the definition of the program volume and program level, we have already seen about Halstead matrix. When we apply it to the testing, so Halstead gives us the effort. We have volume and we have the program level. He says the program level is 1 by n1 by 2 plus n2 by n2. This is nothing but the L, the volume ratio. And this is program 1 by, because this is nothing but what? This is nothing but difficulty. As I said, difficulty and volume ratio are inversion of one another. Effort, E is effort. Effort is E, V is volume, D is difficulty. So if you multiply PL multiplied by effort will give you volume, or you can say effort is volume into the D, difficulty. Now this can be used to find out the effort, but this can be done for the whole software in terms of testing. How much effort you are going to put in. So the percentage of overall testing effort for a certain module K, now with the Halstead matrix, can be computed like this. So this is the percentage of testing effort, and this is given by EK divided by summation of EI. This numerator is computed for module K for each module, and the denominator sigma EI is the sum of Halstead effort across all modules of the system. How many modules? 10 modules. So you have to do sigma 1 to 10. And this is for the module which is concerned, which we are talking about. So this is the percentage of testing effort. Metrics for maintenance. Now whenever you deliver the software or you give various versions, then there will be maintenance. That is, module will be changed, something will be modified. So IEEE standard 982.1/2005, they suggest the software maturity index. It indicates stability of a software product, and this is based on the changes, modification that occur for each version or release of the product. So the changes and modification, maintenance is all about this only. So there is version 1, there can be version 2, there can be multiple version. Every time there will be some module change, will be some module added, there will be some module deleted. So this software maturity index is computed very easy. There are a parameter MT is number of modules in the current release. It can be any version, any release. FC is number of modules in the current release that have been changed. What is FA? See, this is the number of modules in the current release that have been newly added, extra added. FD is the number of modules from the preceding release that were deleted in the current release. So that is the number of modules being deleted. So the SMI is computed like this: MT minus FC plus FA plus FD divided by MT. As this SMI approaches 1.0, we can assume that the product is beginning to stabilize. SMI may be used for planning software maintenance activities. The mean time to produce a release of a software product can be correlated with SMI, and empirical models for maintenance effort can be developed. Okay, this is all about this discussion. Thank you so much and take care of yourself.